So, in terms of the physical properties for carboxylic acids and esters, and also for amines and amides, um, this stuff is stuff that you should be able to kind of figure out based on your previous knowledge, and namely, what we're going to be looking for here are things like hydrogen bonding. Actually, for all of these, that's really going to be what you're going to be looking for the most. So for carboxylic acids and esters, in general, these are going to be polar compounds. The reason I say in general is if they're carboxylic acids or esters that are long enough in terms of their hydrocarbon part, they can actually be nonpolar, have nonpolar properties. But in general, think of these as polar compounds. But only carboxylic acids can undergo hydrogen bonding. So remember, for hydrogen bonding, you're looking for a hydrogen that's bound to an O, N, or F. So right down here, you have hydrogen that can undergo hydrogen bonding. In terms of an ester, you're not going to be able to undergo hydrogen bonding. So for instance, here is an ester where you're looking at the methyl acetate, and you'll see that all the hydrogens are attached directly to a carbon. So whereas in a 3-carbon carboxylic acid, where you have this OH there, that's able to undergo hydrogen bonding. So propanoic acid is going to have a very high boiling point. It would also have a high melting point too if you looked at its melting temperature. In methyl acetate, though, over here, there's no H attached to that O, right? That oxygen is attached to a carbon on the right with the CH3 or the methyl group, and it's attached to a carbon on its left in that carbonyl group. So because of that, esters cannot undergo hydrogen bonding, and they're going to have much lower boiling points than corresponding carboxylic acids. We didn't talk about alcohols. We skipped chapter 12, but in general, it's can be useful to know that if you're comparing an alcohol, which is what this one over here is, 1-propanol, with a carboxylic acid, which is what you have over here with acetic acid, they can both hydrogen bond, right? Both of them, where I have the underline, you can see there's an H bound to an O. But the carboxylic acids are actually going to have slightly higher boiling points because of that carbonyl group there, and specifically that oxygen, because if you look at the shaded point there where it says more hydrogen bonding interactions are possible, remember that for the hydrogen bond, you have a hydrogen that's the hydrogen bond donor, and those hydrogens interact with, the hydrogens that can hydrogen bond interact with hydrogen bond acceptors, which are typically going to be oxygens or nitrogens. And sometimes halogens, but usually oxygens and nitrogens. So because the carboxylic acid has that extra O there, which can act as a hydrogen bond acceptor, it's going to have a slightly higher boiling point than corresponding alcohol. Now looking at amines and amides, oftentimes you can distinguish amines, particularly small molecular weight amines, because they have a really bad smell. Think of fish, rotting fish in particular, urine, bad breath, like all those things kind of have a pungency to them, which doesn't really smell good. And that's all because of their compounds that have amines. Similar to the carboxylic acids and esters, amines are going to be polar molecules. They're going to have polar C-N bonds as well as usually NH bonds, even though if it's a tertiary amine, you won't have any NH bonds. Primary and secondary amines can undergo hydrogen bonding. Remember, primary and secondary amines refer to the number of carbon-nitrogen bonds you have. So down here, you're going to have a primary amine because that's going to be one carbon-nitrogen bond. So when there's only one carbon-nitrogen bond in a primary amine, that means we have 2 different hydrogens that can hydrogen bond. So both of these hydrogens down here are able to hydrogen bond. Right, and because they can hydrogen bond, that's going to increase their boiling points and melting points. Looking at comparing amines to ethers, like for instance, right? Both of these have the same number of carbons. Diethyl ether has 4 carbons, and butylamine also has 4 carbons. Well, butylamine can form hydrogen bonds because of that NH2. This ether molecule Again, the oxygen is bound directly to that carbon and to this carbon. So the oxygen has no hydrogens attached to it, so it cannot hydrogen bond. So that's why butylamine would have a higher boiling point or melting point. So again, you're always looking for hydrogen bonds first and foremost when you're looking at these physical properties and boiling points. And then you kind of look for polar, non-polar, right? If they're both non-polar, you look to see which one's bigger. But again, the main point here and what you're going to be seeing for most of these are going to be in terms of which ones can hydrogen bond versus which ones cannot. Speaking of which, tertiary amines, if you were to compare those to primary or secondary amines, are going to have a lower boiling point. So the tertiary amine is this one over here, right? It says tertiary amine, no NH bond, because that N that is shown there is attached to all carbons, right? It's attached to the CH2, CH3 group, right? An ethyl group. And then it's attached to two separate CH3 groups. Because of that, there's no NH bonds, and that's going to make it have a lower boiling point than, for instance, the diethylamine, which is on the right, that does have an NH bond, right? So that hydrogen circled there is going to be able to hydrogen bond, and that's going to give it a higher boiling point. Now, looking at amides, right? Primary and secondary amides are going to have higher boiling points than tertiary amides or even esters because of that ability to hydrogen bond. So on the left over here, we have an ester, which we talked about earlier, cannot hydrogen bond because there's no H attached to that O I have underlined there. The tertiary amide here in the middle, again, has an N, but it has no H directly attached to it, so it's not going to be able to hydrogen bond. So the ester does have a lower boiling point than the amide, but I wouldn't ask you to be able to compare those two. I'm not worried about that. But what I would expect you guys to be able to do is to be able to look at this one, the primary amide, and because it's able to form, because it has two hydrogens that can hydrogen bond there, I would expect you to be able to tell me that that primary amide is going to have a higher boiling point than that one or of that one. Again, that's just because of the ability for it to hydrogen bond.